All right, this is the start of Unit 7, and in Lesson 7.1, we've got three things I want to do. Yeah, this is going to be intense, so pay attention and follow along. As Unit 7 is actually pretty short, but this lesson is pretty long. Differential equations. You've seen these before, because really they're just equations with derivatives in them. Now, in this course, however, you're only going to be using or solving the simplest type of these differential equations. And the idea behind it is you've got to separate the variables. Okay? There's actually a whole different branch of math called differential equations. When you get to university, you can spend, I guess, your whole degree looking at this stuff if you wanted to. Now, the idea is you're given a derivative and you're trying to find the original function. It's like what we did with anti-differentiation. So remember how we had those questions with a plus c at the end? That's the idea of a general solution. Right? A general solution will be something with plus c. Yet if you want to actually have a particular solution, meaning I want just one particular equation or one curve, then you're going to be given some extra information to help you figure that out. And so the procedure involved really is this. Change all the y primes into dy dx. And the key thing is to separate the variables. So you're going to multiply both sides by the equation by dx. So you can separate the y with the x. And then separate the variables. So move all the stuff with x on one side and move all the stuff with y to the other side. And then once you've done that, it's great because now you can just integrate both sides. That's step 4. And then remember to add c, okay? And then of course solve for y if necessary. Now, here's the thing. If you want that particular solution, there's this initial condition that you can use. You can plug it in and then solve for c. It's the same stuff kind of like anti-differentiation, just another way of doing it. So let's take a look at example number 1. Here we go. We have the equation x plus 2y times y prime equals 0. Like I said, rewrite the y prime as dy dx, and then I want you to isolate things. So I'm going to move the x to the other side first of all. So I get now 2y dy dx equals to negative x. And then I'm going to multiply both sides by dx. So notice I've now separated everything. Okay? Negative x dx on the right-hand side, 2y dy on the right-hand side. Once you've done that, now you can do step 4, which is integrate both sides. So 2y dy, the antiderivative there is y squared. The antiderivative of negative x is negative x squared over 2. And then don't forget, plus c. Okay? Now it does say to add c to one side, but technically you could have two c's on both sides, but they're different constants. Why don't we just put them together as one c? It just makes it easier. Good. Now, unfortunately, we need to solve for y, not y squared. So really our next step is to solve for y. Now, if I solve for y, you'll notice that you get the following. Most people just write this down and I'm like, that's wrong. It actually should be plus or minus. But with a plus or minus, you actually don't have a function. So I have a little blurb here that says, write your solution to example 1 as a pair of possible functions. So really, you need to write them as two separate functions. And here are the functions, the positive square root, or we can use the negative square root. Okay? Now, here's the big note. Yes, you should write this down. These are written separately, and there's a reason for that. Why? Well, because the solution has to be one or the other. It has to be a function, right? It has to just give one y value for each x value. So because the solution is either one or the other function. But here's the thing, but not both. Because when I have both, it actually is not a function, it's a relation. Okay. All right, so just be aware of that. You're going to choose one of these parts if you get a situation where you have this plus or minus square root. Okay, let's take a look at example number 2. Find the equation of a function of the form. Okay, so you want to solve for y. Got that. This time I gave you some more information. 0, negative 3. So with that, you should be thinking, I can get rid of that c value. That is correct. And it says whose slope, hey. Can you say dy dx? That's slope. Whose slope is x to the e to the x squared over y. Okay, for each point on the curve. Same thing, friends. Let's separate. I'm thinking we'll multiply both sides by dx. So I get x e to the x squared dx. And then technically there should be a y over here, but I could move that to the left side, and that just becomes multiplication, so just y dy. Okay? Great. Now you're ready to anti-differentiate. So when I do that, what do I get? Y squared over 2 on the left-hand side. And on the right-hand side here, I'm thinking, oh, I see u substitution. Yeah, du dx, 2x. That just means, hey, x dx is du over 2. Yeah, this is great. Running out of space, but that's okay. E to the u, and then it's du over 2. So if I anti-differentiate, I get 1/2 e to the u, and that's just x squared. So yeah, more practice with u substitution. And don't forget, that's right, plus c. And I guess you're supposed to solve for y, so you can multiply both sides by 2, so you get y squared equals to e to the x squared, I guess, right? Plus, and multiplying the constant by 2, I guess you can call it c sub 1, because it is a different constant. Or if you just want to just call it c, that's okay too. So it doesn't really matter. It's still a constant, right? Cool. Now, you're supposed to solve for y, so once again, plus or minus the square root of e to the x squared plus c. But you can't quote both of those answers for me. No, that's no good. Looking at the thing that I highlighted, do you see that the y value here is negative? So do you know which one I should actually take? Yeah, you're right. I should just take the negative root. And if I do that and plug in the values, you should be able to solve for c. So the negative cancels out. E to the 0 is just 1. I'll square both sides. I get 9 equals 1 plus c, and then I can solve for c, that is 8. And therefore, the equation is y equals to negative square root of e to the x squared plus 8. That is my particular solution that contains the point 0 comma negative 3. Okay? Now just a few notes here, okay? Why did I choose a negative square root again? Because the initial y value is negative. Okay? Now, just to let you know, above I kind of said, well, I skipped it over, but steps 5 and 6 are interchangeable. So really what I did was I solved for y first, and then I plugged in the point. But as an alternate method, I could have plugged in the point first. Shocking, eh? So I could have just taken this step here, okay? And without doing all the rest, I could have just said, oh, let's plug in the point first. So 0 squared, oops, my fault, y, right? Negative 3 all squared equals e to the 0 squared plus c. And once again, you would have found that this is 9, this is 1, so the c value is 8. Yeah. And then I could have subbed it back into where I had it, so y squared equals to e to the x squared plus 8. And then from here, take the square root, and then once again, you don't want the plus or minus, you only want the one that actually works in this case, which is the negative component. That works too. Okay? Once again, doesn't matter where you do it. I'm thinking on the AP exam, if you were to do this alternate method, it might be actually easier because maybe you won't make an algebraic mistake. But once again, it doesn't really matter if you're doing things right. The answer will be the same. Okay. All right, turn the page. Here's example number 3 for you. Okay, so solve this differential equation this time, and I did give you a particular point, so you should be able to get rid of the c value. You're thinking, oh, I'm going to leave the x's on this side, and I'm going to move the dy over. Here's your dilemma if you do that. By the way, don't write this down, because it's wrong. Your dx and your dy can't be in the denominator. It actually has to be level or in the numerator, right? So, and this is no good. Unless you actually take it and flipped it, then it'd be okay. So really flipping it and making it dy over y minus 2 and dx over x. That is okay. Okay, now if you didn't want to do that, you could have just said, hey, I'm going to take this dx and move it over first. So y minus 2 times dx equals x dy. And you're like, but this is wrong because they're not separated. I get it. Then you can actually move the x over to this side and then move the y minus 2 to the right-hand side. So once again, you get dx over x and then dy over y minus 2. Okay? So it doesn't matter how you get to this step, just get to this step because now things are separated and now the dx and dy are in the right position. Okay? So copy this down now if you haven't done it already. Pause the video to copy this down. Okay, so I'm going to use this red piece here, and I'm going to rewrite this as 1 over y minus 2 dy equals to 1 over x dx, because now if I take the antiderivative, oh, you're like, I know. Natural log of y minus 2 equals to natural log of absolute value of x plus c. Good. Now, I'll show you both methods now at this point, okay, because I don't know which one you like better, but I'll show you both, okay. Let me go over here and call this method number 1. And what I'm going to do now is actually plug in the point first. Plug in point first. Here we go. Ln of the absolute value of half minus 2 equals ln of absolute value of 1 plus c. That just becomes c. Half minus 2 is negative 3 halves, but I want the positive version of it, so natural log of 3 over 2 equals to c. Ah, nice. So now, if I ask you to solve, you now have this equation. So therefore, you have natural log of the absolute value of y minus 2 equals natural log of the absolute value of x plus natural log of 3 over 2. Now, let's take a look. We need to get rid of this to solve for y. So we will now e both sides. And if I do that, you're left with y minus 2 on the left. And then what do we have on the right? We have here e to the ln of absolute value of x times e to the ln of 3 over 2. Now you have to be a little bit careful here. I'm going to say to you that this is going to be this part here. Is it x or negative x? I hope you can realize that this just becomes y minus 2 equals to negative x times 3 over 2. Remember, e and ln cancel each other out? But why is this negative x? Well, what's y minus 2? Isn't that going to be less than 0? So why is this negative here? Because I'll say y minus 2 is less than 0. Keep going now. We'll get y minus 2 equals to, I guess I don't have to go y minus 2. I should just solve for y. So y equals to negative 3 over 2x plus 2. And there is your answer. Okay. Now, if you didn't want to plug in the point first, I'll show you method number 2 over here. Method 2. You would have then taken this expression that I'm going to highlight in blue. Remember this one we left off there? And we're going to now e both sides right away. Okay, so we'll e both sides. So you'll see you get this e to the natural log of y minus 2 equals to e to the natural log of absolute value of x plus this c value. And be careful here. This is e, and this whole thing is a power. So we can rewrite this as e to the natural log of the absolute value of x times e to the actual c. And e to the c, of course, is another constant. So we can just call that another constant. So in essence, we have here y minus 2 equals to that. We can have this equaling a constant. Let's call it capital C. Okay, that capital C actually puts a plus minus in there because of the absolute values. And so now we have C times what? Well, e to the ln x, of course, is just an x. So we have this. Okay. But remember, this plus minus c thing is really just another constant. So do I need a plus minus? Not really. I just call it a constant. Okay. So y minus 2 equals to that. And then now I have y equals to cx minus 2. But how do I solve for c once again? Well, this is where I'll plug in the values. So now I'll plug things in. So 1/2 equals to 1c minus 2. And c, of course, equals to 3/2. Oh, sorry, plus 2. My fault. Plus 2, plus 2. Sorry. So c equals to negative 3/2. Right? 1/2 minus that. And then once again, you get the same equation. Ta-da. Okay. So it doesn't really matter, right, what you do. But both methods will give you the same answer. Okay? All right. You might see some other algebraic equations like this, and I've seen this on the AP exam recently, so maybe not number 4, but number 5 for sure. So number 4 is really not anything related to calculus, but hey, is this a solution? Well, all you need to do is, of course, plug it in, right? So you plug in negative 2. You're hoping that the left side equals to the right side. Does it? I think so. So yes, x equals to negative 2 is a solution. So if they give you a question like this, is this y value, y equals to 1/2 e to the x plus e to the negative x, a solution of this differential equation? Well, all you need to do is, yeah, the same thing as what we did before. Plug it in. But this one involves y prime, so I guess we should calculate y prime first. Y prime is just 1/2 e to the x, and then this is what? Minus e to the negative x. And so your question now is, let's plug it in. So here's my y prime, 1/2 e to the x minus e to the negative x. That equals e to the x, and then subtracting off y, which is just my original function. Do we get the same thing? Do we get the same thing? Do we get the same thing? I think we get the same thing. So yes, it's the same. So yes, it is a solution. If it's not the same thing, then nope, not a solution. Okay. Now notice you don't have to actually, this is not a separable differential equation, right? This is not something I can separate and solve, because if I were to try that, don't write this down, but if I were to try that, I'd run into trouble, right? Can't do dx, that'd be e to the x minus y dx, and then now I'm stuck, I can't actually just take the y over, I'm going to be in problems. So, not a differential equation, okay? All right, topic number 2. So, you've been thinking about the pandemic, perhaps, with COVID. You've been hearing about exponential growth and decay. Here's a chance to actually look at it and where it actually comes from. Mathematical models in which the rate of change of a variable is proportional to the variable itself, so it's like replicating itself, are common in both business and scientific worlds. And so what you see when I say the rate of change, remember this word rate of change? Hey, that's the derivative. When I say it's proportional, that means it's some value of k or some constant multiplied by the variable itself. That's the y. So we have this differential equation, dy dt equals to k times y. Now, what can we do with this differential equation? Well, we just learned how to separate that. So we can actually do that on the next page. So can we separate this? I think you can. We'll do now by multiplying both sides by dt. And then remember, I want to isolate the y, so I want to divide the y. So dy over y now equals to k times dt. There you go. You separated the variables. And so now we're going to anti-differentiate. Natural log of the absolute value of y equals to k times t plus c. Remember, k is a constant. And then if I both sides now, once again, I just get to the natural log of y, which is y. And I get to the, what happened there? To the kt plus c, which really is the same thing as y equals to to the kt times to the c. And of course, that to the c is just a constant, so c to the kt. Look at that. The box below is what we call the basic law of exponential growth and decay, and this is the equation that follows suit. So what I want you to realize is, look, when you're given this differential equation, dy dt is equal to k times y. When I solve for y, we automatically get this equation, y equals to c, some constant, times to the kt. So once again, c is the initial value, it's the initial amount of substance. K is the constant of proportionality that gives you like the rate. Okay? And the variables here are t for time, and y is the amount of whatever substance you're talking about. Okay? So looking at example number 7 now, I'm going to ask you to apply this. It says, what is the rate of growth of the population in a city whose population triples every 100 years? And I did say that you can assume population growth can be modeled by the basic law of exponential growth, meaning you know that it follows this form of dy dt equals ky, meaning, so you can go straight and say, oh, it must have an equation of this form. Okay? So now let's see if we can solve this. Let's see. The population triples every 100 years. So I guess if I started with the initial population of, like, say, p, then tripling, meaning after at the end, that y value will be 3p. And then we have to the k, and I guess the years is 100. Well, this is nice because the p's just cancel each other out. Yay! And you get 3 equals to to the 100k. And you need to solve for k, so I'll take natural log on both sides. Natural log of to the 100k is just, it's just 100k. Woohoo! 100k, I'll take 100k. And what's my value of k? Yeah, log 3 over 100. So I guess r is equal to, I guess this is where you bring a calculator. I don't know what this is either. Log 3. Close the bracket, please, and then divide by 100. Oops. 100. Da, da, da. That's about 0.109 or approximately 10. No, not even 10. I missed the 0.019. So, about 1.09 or 1.10, I think. Yeah, it's 986. 1.10. Okay, rounding between this 100%. Good. Oh, last one. Oh, how about this one now? It says let Y represent the mass in pounds of a radioactive element whose half-life, sounds like chemistry, yeah, whose half-life is 4,000 years. If there are 200 pounds of the element in an inactive mine, can you tell me how much will still remain in 1,000 years? Wow. Express your answer this time to 3 or more decimal places of accuracy. Okay. So you're going to go ahead and use that exponential growth and decay equation again. So y equals c to the kt. This time I'm thinking half-life is 4,000 years. So if I started with p, and half of p would be what is at the end after what? 4,000 years. So to the k times 4,000. Wow. Okay. So this first part is the same as what we did before in the previous question. So I'll start stopping off. Actually, I'll stop talking and let's see if you can do this yourself. Okay, at least solve the k first. Okay, go. Take natural log. Divide by 4,000. And that's your k value. Now, at this point, I actually wouldn't round. I'd actually keep this as my k value. And so now I have the equation, therefore it being y equals to c e to the k. Oh, wait. You know what k is, right? K is natural log of 1/2 over 4,000 t. Now we can use the rest of this. If there are 200 pounds of element in an active mine, how much will remain after 1,000 years? So let's go ahead and plug that in. 200 e to the natural log of 1/2 over 4,000. And we're multiplying this by 1,000. So I can simplify that. E to the natural log of 1/2. And 1,000 over 4,000 is just 1/4 or divided by 4. And then this is what I would plug into my calculator now, 200 times e to the power of bracket natural log of 1/2 divided by 4, close the bracket. Boom, 168.179. 168.179. And don't forget our units, pounds. Okay, that's it for this one. Your turn to practice. After that, we'll come back and we'll do lesson 7.2. We'll see you then.